Phase kickback is a very useful concept in quantum algorithm design. It provides a framework to understand many famous quantum algorithms, such as Cirq algorithm, the phase estimation algorithm, Doshi algorithm, Simon's algorithm, etc. In this video, we shall explain the concept of phase kickback and also demonstrate the phase kickback in Cirq and Qiskit. The main idea of phase kickback can be illustrated with this two-qubit system. U is a controlled unitary gate whose action on the target qubit depends on the state of the control qubit. If the control qubit is in state 0, then nothing happens to the target qubit. If the control qubit is in state 1, then the unitary gate will be applied EI5 to the target qubit. In order to implement the phase kickback, we need to apply a Hadamard gate on the first qubit. So looking at psi 1 over here, after the Hadamard gate, we have a superposition state on the first qubit, tensor with the second qubit. If we apply a control unitary gate on the first and the second qubit, if the first qubit is 0, then nothing will happen to the target qubit. So we have 0, 0 here. But if the first qubit is in 1 state, then it will apply an EI5 to the second qubit. And if we do a regrouping, we'll get to this. And you can see that now there is a phase applied to the first qubit. And if the phi is pi, then EI pi is -1. In this case, we will have 0 minus 1, and this is after the Hadamard, we'll get 1, 0. So we can see that the first qubit have flipped from a plus to a minus. So this effect is known as the phase kickback. Let's look at some examples of phase kickback. The first example is a CNOT gate sandwiched between a pair of Hadamard gates. So at this point, psi 1 is given by plus state and minus state after the two Hadamard gate operations. And the plus can be written in this way. And after the CNOT, the 0 will have no impact on this second qubit, but the 1 will flip the second qubit and end out there is a minus sign in front. And if we group again, we will have minus minus. And after we apply the Hadamard gate again, we will get 1, 1. So from 0, 1, we end up with 1, 1. So it seems that now the second qubit seems to flip the first qubit. So this can be written in this way. The second qubit it now seems to flip the first qubit, so the C0 seems to be inverse. In fact, it can be shown that this is true for all possible scenarios, and we shall demonstrate that in the code later. So this is one example of phase kickback. Another example of phase kickback is the Doshi algorithm in the previous video. So Doshi algorithm can be implemented by this oracle, where we have two input x and y, and two output x and y XOR the fx. In Doshi algorithm, we want to check whether this f is a constant or a balanced function. Take an example where y is equal to this minus state. So this oracle is applied to x and minus, and the minus we can expand out in this way, and we apply this oracle on this whole system. We'll get to this x and 0 plus fx and minus 1 XOR the fx, and this can be written in this compact form. The reason is given here. When fx is 0, we'll have 0 plus 0 is 0, 1 plus 0 is 1, so we get x minus, and when fx is 1, we get 0 plus 1 is 1, and 1 plus 1 is 0, and that turns out to be minus. It just turned out to be the reverse of the previous case. That's why we can write in this compact form. And if you compare this output with the input, we see that there is a phase kickback to the first qubit. This is the main reason why the Doshi algorithm can check whether this f is constant or balanced with just one query. Now let's demonstrate phase kickback in the code. Let's demonstrate on the Cirq first. We have this 2 qubit system. We apply a pair of Hadamard gate, followed by a CNOT gate, and followed by a pair of Hadamard gate. And we check what is the unitary matrix. We get 1 here, 1 here, 1 here, and 1 here. The rest is all 0. And now we want to prove that this circuit is the same as this CNOT circuit, but with the control on the second qubit and the target on the first qubit. So we'll construct this circuit, and then we check the unitary matrix. Again, we see that this matrix is identical to this matrix. That's why these two are exactly the same due to the phase kickback effect. And this can be also implemented in Qiskit. So we import the Qiskit library, we construct the circuit, and this is how the circuit look like, and we print out the unitary matrix. We get 1 1 1 1 here, and we can also take a look at another circuit with the reverse CNOT with the control at the second qubit, at the target at the first qubit, and then we print out the unitary of this circuit, and it turns out to be exactly identical. So this circuit is the same as this circuit, And the main reason behind it, as we said before, is due to the phase kickback effect. This concludes the video on phase kickback. The code is given below. If you liked the video, please share and subscribe to our channel. And if you like to comment on the video, please share your comment below. Thank you.